Okay, welcome back. Hopefully you got the general idea of how this works with the last video. We'll do a couple of other ones, shapes here from the extended octet family, and then we'll move on from there. Alright, so let's do one from the AX5 family. 5 shared pairs, no unshared pairs. Main shape, trigonal bipyramidal. So let's take a look at an AX3E2, and I'll let you fill in the rest. An example of an AX3E2 here would be, this is a chlorine trifluoride. It's a covalent compound, two nonmetals there. Side note, this is just seriously nasty stuff. You don't ever want to mess with this one right here. This is a more powerful fluorinating agent than fluorine gas. I'm not sure you know enough chemistry to fully appreciate what I just told you. The Army, actually, I guess it was the military, they were considering using this stuff as an oxidant for rocket fuel. Extremely powerful oxidant. They thought it was just too dangerous to deal with. That's how bad this stuff was. There's a story, written account of a spill of 1 ton of this stuff back in the 1950s in a room. It ate through the concrete floor, through the slab, through the gravel underneath, and into the rock below before it finally burned out. Bad stuff. You don't want to be anywhere near this. This will oxidize concrete and chemistry students as well. There's some things out there, I won't lie to you, there's chemistry can be dangerous, and there's some stuff out there that if you get a whiff of it, yeah, it'll turn you into a vegetable pretty quick. And there are people who are willing to work with stuff like that, and they get paid a whole lot of money to work with that stuff. I am not one of those people. I just really don't want to do that. This is how I live to be 53, is not dealing with stuff like chlorine trifluoride. But yeah, this is look kind of harmless sitting there on the paper, right? But yeah, bad stuff. Okay, well anyway, historical note. So what does it look like if you drew the dot structure? Well, if you drew the dot structure, it would look actually something like this. You've got 3 fluorines here. This is 2 pairs of electrons. It's just kind of a little sketchy there. But this is an AX3E2. 3 shared pairs, 2 unshared pairs on the central atom, and I left out the dots around the fluorines. You can put those in if you want to. Okay? Alright. This is an expanded octet molecule because you have 5 pairs around the chlorine, so therefore 10 electrons, so that's more than 8. It belongs to AX5 family because there's 5 pairs around it. They're just not all shared. Okay, AX3E2. So the electronic geometry of those 5 pairs would be considered trigonal bipyramidal. Okay. The molecular geometry of this, however, is actually T-shaped. So how do I get the T-shape from that? Well, what you do is you take that trigonal bipyramidal that we started with. That's my AX5. Save time, I went ahead and built it again here. So basically with AX5s, what you do is you essentially pull off all the equatorials. So if I wanted to have an AX4E, by the way, I just pull off one of those equatorials, and they call this seesaw. Why do they call this seesaw? Well, because if you turn it this way, it's kind of like a seesaw. You've got a kid over here, you've got a kid over here. So yeah, that's an AX4E. That's your seesaw. But to get to the AX3E2, what you do is you take off another equatorial. And now you've got a shape they call it T-shape. I'll let you guess as to why they call it T-shape. But this is what chlorine trifluoride looks like. Alright? You could draw it, and you could draw it, well, in the shape of a T if you want to, because I guess that's literally what it looks like. You could draw the trigonal bipyramidal, see, and then just erase 2 of these, and then, see, there's your T right there. Okay? Bond angles. Well, the bond angles of an AX3E2, since it has the same electronic geometry as trigonal bipyramidal, are going to be the same as the trigonal bipyramidal. It's just that in this case I have my 180, which goes from here to here, and I have my 90, but I don't have any 120s here. So your bond angles for this are 90 and 180. All right? So do you see that the bond angles for the shapes in the same family are the same bond angles as the main shape? So if you know the main shape, you're well on your way to memorizing the rest of it. Okay? If you had an AX2E3, by the way, take off your other equatorial, and you're back to linear, just like an AX2. See? And the reason this is linear is because I have these three pairs of electrons here around the center. These three pairs here are forcing this atom that way, and they're forcing this atom that way. So it's just like an AX2. You're back to linear. Of course, your bond angle is 180. Okay? All right. Well, let's take a look at one from the AX6 family. Of course, the main shape there is octahedral. And this one actually got pushed down to the next page and never did get copied. Sorry about that. So, in fact, that is off screen, isn't it? Hang on a second. Let me see if I can. There we go. That's probably a little better. Okay, so let's take a look. The AX5E is something called square pyramidal. And the way you derive this is you look at your octahedral shape. But with the octahedral ones, what you do is instead of taking off equatorials, you take off your axials. So this is your AX5E. And it looks like this. And this is called square pyramidal because, again, take a look at the solid shape that's formed. So you've got a pyramid here with a square base and a triangular face here in front, one in the back, one on the right side here, and one on the left side here. And so it's just like a pyramid out in Egypt is sitting in the sand. So I got a pair of electrons here, but when I name the shape, I ignore that. I look at what's left over. Okay, and that's square pyramidal. All right. The one I want to look at is this one right here, which got left off, and that's that AX4E2. All right, AX4E2, 4 shared pairs, 2 unshared pairs on the central atom. What would be a great example of that? Well, here's that xenon tetrafluoride. Remember that dot structure we drew? That was the first expanded octet dot structure we drew, xenon tetrafluoride. Well, it turns out it's an AX4E2 because, see, I've got 4 shared pairs, and 2 unshared pairs on the central atom, and of course draw your electrons around for the fluorines if you want to. Okay? The shape of this is square planar. And the way you make it is take off this bottom axial, take off this top axial, and you're left over with that, which essentially is a big flat square. These atoms are in the same plane. That's what we call a square planar. Okay? Now, why is this flat, and how come CH4 is tetrahedral? Well, because in this particular case, you have a pair of electrons up here which is forcing these 4 atoms down. But at the same time, you have a pair of electrons down here which is forcing these 4 atoms up. So where do they end up? In the same plane, right here in the middle. Okay? And that's why this ends up being flat and square planar. So when I said molecules are not flat, they're 3-dimensional, just like you and me. Well, sometimes they are flat, I guess. Yeah, and here's a case where you've got one that's actually flat. And that's what xenon tetrafluoride looks like. Your xenon's in the middle, and your 4 fluorines are there around the outside. Okay? There's a couple other shapes in the AX6 family, but you don't really run into those very often. So I'll tell you what, if you can just do AX6, AX5E, and AX4E2, we'll call it good from the AX6 family. All right? So the lone pairs of electrons do influence the geometry. You just don't look at them when you name the shape. But they're there, and they do influence the geometry. And there is a nice little picture, I believe in your book, of everything here. See, there's your bond angles, 90 and 180, of what I've drawn. Here are some dash line wedge stuff, and these are actually the orbitals, which we'll talk about maybe in the next chapter. But basically, here's your AX2, linear, trigonal planar, tetrahedral, dash line wedge, trigonal, bipyramidal, and there's your octahedral. Those are your main shapes in the family. And we say they have an electron pair geometry, AX5, AX2, AX3, AX4, AX5, and AX6. Okay? And then there's also a nice little picture here somewhere of different shapes here. And you can look at that chart as well. And they draw a whole lot better than I do. But yeah, take a look at that if you want. Fill in the rest of your chart with some examples that you can find. And then that way you've got everything in one spot. Whoa, everything in one spot, and you can study a lot easier with it that way. Okay? All right. Well, that takes care of that. So what do we need to talk about next? Well, let's talk about multiple bonds. Okay, we've all dealt with all these molecules with single bonds. What if I got a double or a triple bond in there? Well, if you see a double or triple bond in the molecule, you pretend like it's one bond for the purposes of determining your VSEPR formula. There's a reason why. We'll talk about it in the next chapter. You just have to use your imagination. So, therefore, this BF3, which looks like this, that's an AX3, 3 shared pairs, no unshared pairs on the central atom. Here's that expanded octet SO3 gas molecule, this neutral there, and it looked like this, if you'll remember. This is not an AX6. This is an AX3, just like BF3. See? This counts as one pair, this counts as one pair, this counts as one pair for the purposes of your VSEPR formula stuff. I know it's not one pair. And for the purposes of determining how many electrons you have around an atom, I know it counts as 2 pairs. But you just have to pretend for the purposes of doing VSEPR formulas. It will make sense next chapter, but that's what you do. All right? Just practically, why does it work that way? Well, think of it this way. Let's say, for example, I have... if I can build one here real quick. So here is my SO3. And we said it was trigonal planar, right? So that's a pretty close approximation, I guess, of trigonal planar. So what's the difference between an SO3 molecule that had all single bonds and an SO3 molecule that has double bonds? Well, double bonds are stronger and shorter than single bonds. So essentially, it's this. Okay? Now, when I did that, did I change the shape of this molecule? Not really. I just went from a bigger triangle to a smaller triangle. See, it's trigonal planar. So what that double and or the triple bond does is it just simply shortens the bond. It doesn't radically change the shape of the molecule. So therefore, you essentially just pretend like they're one pair. So if you see a double bond or a triple bond, for the purpose of determining your VSEPR formula and therefore your shape, pretend like it's one pair. So instead of saying the number of shared pairs of electrons around the central atom, perhaps it would have been better to say the number of groups of shared pairs around the central atom. You want to think of it that way, you can. Okay? Both those are AAA. Here's a BF3. That's an AX2. See, 2 shared pairs, no unshared pairs. That's linear. Here's a CO2 molecule, and it looks like this. That counts as 1, that counts as 1. So both of these are AX2 molecules, and they're both linear shape. And so CO2 is what you're breathing out. You're actually breathing out a bunch of little tiny lines there. And that's what it looks like. Okay? And that's how you deal with the multiple bonds. All right? Side note here before we go on. Here is a NH3 molecule that we talked about earlier. And we said this was an AX3E because you had that unshared pair of electrons sitting there on that nitrogen atom, right? Okay. How did I know there was an unshared pair of electrons on that just by looking at the formula? How do I know there's 2 unshared pairs of electrons sitting on this oxygen just by looking at the formula H2O? And there's none sitting on this CHCl3. Because that's kind of important. Because remember, your VSEPR formula is the number of shared pairs and unshared pairs on the central atom. If you had called this an AX3, you would have got the wrong shape. It's an AX3E. So how do I know that this is sitting here? just by looking at this? I don't. I don't know that. What's the only way you can know there's an unshared pair of electrons sitting there? You've got to draw the dot structure. Draw the dot structure. Don't get lazy on it. Don't just assume this is an AX3 because there's nothing sitting there. No, you're not showing the unshared pairs when you write the formula. The only way you'll know for sure is you've got to draw the dot structure. So you've got to be able to draw dot structures. You can't draw dot structures. You can't get the right Vesper formula. I don't care how well you know this chart. If you don't have the right Vesper formula, you're going to miss the shape. And by the way, if you miss the shape, you're probably going to miss what we're going to talk about next. Everything here keys in this chapter on being able to draw the correct dot structure. Now, you drew NH3 last night, and you drew it 57 times, and every single one of those times there was an unshared pair of electrons sitting on that nitrogen, and you just know it, then that's fine. You don't have to draw it again. But if you're not sure, draw the dot structure, because that's really the only way you'll know if there's an unshared pair of electrons sitting there or not. Okay? Okay. All right. Last thing. Let's talk a little bit about polarity here. Okay? So, you have polar molecules, you have nonpolar molecules. How do you know if a molecule is polar or nonpolar? Well, the short answer is you look at the bonds and see if they're polar or nonpolar. So, I guess the next question would be, how do I know if the bonds are polar or nonpolar? Well, it's actually pretty simple. What it comes down to is this. All bonds are polar unless the two addicals joined are exactly the same, identical, like a hydrogen-hydrogen bond or a chlorine-chlorine bond. So all you have to be able to do is take a look at two atoms and tell me if they're the same or different. If you can do that, if you can tell me if two things are the same or different, you can do this. You can be an expert in bond polarity. Okay? All right. The difference, or the extent of the polarity depends on differences in electronegativity. So I guess your next question would be, what is electronegativity? So maybe that's what we need to talk about first. Okay? Well, electronegativity is the measure of attraction an atom has for electrons in a covalent bond. All right? It's a measure the attraction has for the electrons in the covalent bond, not its own electrons. That's electron affinity. We talked about that in a couple of chapters, last chapter, I believe. All right, this is a little different. It's just that pair of electrons that are being shared with something else. All right? The trend for electronegativity, yes, there's a trend here, is electronegativity increases toward fluorine in the periodic table. Okay? If you look in your book, there's probably, and sometimes they will actually put it in a periodic table kind of chart form there, but there's a chart of what we call Pauling electronegativity values, and it's a ranking of electronegativity of elements. The most electronegative element is fluorine, which has a value of 4.0, and then they go down from there. All right. Do I expect you to memorize Pauling electronegativity values? No. I will give you Pauling electronegativity values for elements as you need them on the test. All right. However, you can still do electronegativity even if you don't have the values, because it turns out the closer you are to fluorine in the periodic table, the more electronegative you are. All right. So, for example, here's a periodic table of the elements. So here's fluorine. So which element is more electronegative, sulfur or sodium? Here's sulfur. Here's sodium. Which one's closer to fluorine? Fluorine is more closer to fluorine. Or rather, sulfur is closer to fluorine. So sulfur is more electronegative than sodium. Which is more electronegative, a zinc atom or an iodine atom? Well, iodine seems a little closer than zinc, and so therefore iodine is more electronegative than zinc. All right. Which is more electronegative, an oxygen atom or a chlorine atom? Well, it turns out it's oxygen. But they're both sitting right up next to fluorine here. So would I ask you something like that on a test? No. I'm not going to ask you something that's like just a coin flip or something like that. But if you looked up the Pauling electronegativity values for oxygen and chlorine, you'll see oxygen actually has a higher value than chlorine. And so it actually is. All right. But I wouldn't do that. But if I gave you phosphorus and tungsten, yeah, you could tell me phosphorus is because it's closer to fluorine in the periodic table. See? So if I gave you anything like that on a test, if you know the trend, you will immediately be able to tell. If you need the Pauling electronegativity values, I will give you the Pauling electronegativity values. You don't have to memorize those. You just have to be able to use them. Okay? Okay. Well, that being the case, let's take a look at this. So here's a bromine, here's a bromine, here's a bond. Okay? And here's that pair of electrons that's sitting between those two bromines that forms that covalent bond. So think of it in terms of like a tug of war. So I've got this bromine which wants to pull that pair of electrons toward it, but I've got this other bromine which wants to pull that pair of electrons toward itself as well. All right, so it's kind of like a tug of war. But it's a tug of war between two teams of equal strength. See, both of these bromines have the same electronegativity. So if I have a tug of war between two teams of equal strength and maybe a little rope on the flag, a little flag on the rope in the middle, which way does the flag move? Well, it doesn't. It stays right in between, right? So where I'm going to find this pair of electrons is I'm going to find them exactly halfway between these two bromines. Here's a case where I have equal sharing of the electrons. It's 50-50 sharing. We call this a nonpolar covalent bond. All right? And the difference in electronegativity here is 0 because it's what the same two atoms. Okay? All right. Here's a hydrogen atom. Here's a nitrogen atom. So it's another tug of war. Here's this pair of electrons. Only this time, which one's more electronegative, nitrogen or hydrogen? Well, the nitrogen is more electronegative. Why? It's closer to fluorine here in the periodic table. Okay? So now I've got a tug of war, but this time it's between two teams that are not of equal strength. The nitrogen team over here is a little bit stronger than the hydrogen team over here. All right? So if I have a stronger team over here in a tug of war and a weaker team, a flag on the rope in the middle, which way does the flag move? Well, it moves over here toward the stronger team, right? So when I look at this pair of electrons here, what I'll find is instead of being halfway in between, it's a little bit closer over here to the nitrogen. So I'm sharing the pair of electrons over here between the hydrogen and nitrogen, but the nitrogen's taking a little bit more. Can you share something and not share it equally? Sure you can. You know, if someone says, can I have a piece of your chocolate cake, do you have to cut off half of it and give it to them? No, you can cut off a little tiny bit, right? Keep most of it for yourself. There you go. That's what's going on here. So it's sharing, but it's not equal sharing. We call this a polar covalent bond. All right. Now, why is this considered polar and the other one nonpolar? Well, pretend like you're a little tiny person and you're able to sit on this side of the molecule, or you can sit on this side of the molecule. Where would I experience more negative charge? Being over here or being over here? Well, over here, okay, by the nitrogen. And the reason why is because this pair of electrons here is closer to me. If I'm over here, this pair of electrons is further away. So this side is kind of like the partial negative side of the bond, and this is kind of like the partial positive side of the bond. Now, all the little squiggly means there, it means partial. It means it's not a plus 1. It's not a 0 either. It's somewhere between 0 and plus 1, or 0 and minus 1 for the little partial negative. That's all the squiggly means. Don't get too worried about all that. Okay? But that's the case. Do you see that this is kind of like a little magnet? It's got kind of like a North Pole and a South Pole. You got a positive end to this bond and a negative end to this bond. Well, that's why we call it a polar bond. Here, if you're here or here, you're equidistant from the electrons in the middle here, so therefore there is no net positive and negative side. That's why we call it a nonpolar bond. So how do I determine what's positive, what's negative? Well, here's the easy way to do it. Draw an arrow toward the more electronegative element. In this case, that would be nitrogen. Put a little plus, see, over here on this side over here. This is the positive side of your bond, and that's the negative side of your bond. The larger the difference in electronegativity, the stronger your magnet, the more polar the bond is. And that's kind of the way it works. Okay? Okay, well, here's a sodium atom. Here's a chlorine atom. Here's a pair of electrons. Which one is more electronegative? Well, chlorine. And it's sitting right here underneath fluorine, right? Where's sodium? way over here. Not very electronegative at all. So again, we have a tug of war, only this time it's between a team of firemen over here and a team of fourth graders over here. Who's going to win the tug of war? Well, the firemen are going to yank those little fourth graders all over the place, right? This chlorine wants that pair of electrons so much, and this sodium really doesn't care. The chlorine just says, I'm going to take them. And so now this pair of electrons actually belongs to the chlorine. There's no sharing here whatsoever. So if there's no sharing here whatsoever, what keeps them together? Well, this sodium now has one less electron than what it had before, because its electron went with the chlorine here. So what's the charge on it? Well, it's +1. This chlorine now has one more electron than it should. What's the charge on it? -1. What keeps them together? Well, the fact that you have opposite charges, and opposite charges attract. What is that? Folks, that's an ionic bond. That's an ionic bond. Do you see that polar covalent bonds are kind of the gray area between pure covalent bonds, where I have equal sharing, these nonpolar covalent, and ionic bonds where I have no sharing? No charges here, +1, -1 here, unequal sharing, partial plus, partial minus, polar covalent. Okay? Now, how do I know if it's ionic or if it's polar covalent? Well, most ionic bonds are not really pure ionic bonds. There's some ionic character to them, and there's some covalent character to them. When your ionic character becomes greater than about 66% and 34% covalent character, we just go ahead and classify those as an ionic bond. All right? The way you tell is you go back and you look at those Pauling electronegativity values. If you can subtract those two values and you get a number greater than 2, it's ionic. Okay? That's just the rule, standard. Okay? If you get a difference in electronegativity between 0 and 2, then it's polar covalent. Okay? Now, your book, and some books will do this, may make an exception there. What they'll say is if it's between 0.4 and 2, they're going to classify it as polar. I understand that. If it's under 0.4, it's so weakly polar, they just call it nonpolar, and there's no reason why. But really, technically, if there's any difference at all, it's polar. So I usually just say between 0 and 2. You know, if your book disagrees with me, then, you know, what are you going to do? You can go either way. You want to go with mine or you want to go with the book, you know, that's up to you. But that's what I say. That's what I do. Up to you to do whichever one you want to learn. So, but yeah, that's kind of the way it goes. If there's no difference in electronegativity, then it's considered nonpolar. But I will say this. Really, it's possible to have two atoms that have the same electronegativity, but the bond is still polar. For example, a carbon-iodine bond. You look up the electronegativities of both of those, it's exactly the same. But that bond is actually polar. The negative charge is on the iodine because of differences in what we call polarizability. Polarizability is the ability for an atom to alter its outer electron distribution. For example, if I had an atom like this, the styrofoam, it's hard. We literally call them hard atoms. The electrons are just kind of stuck around there and they don't really, move. Imagine a little Nerf ball, a little squishy rubber ball. Okay, we call those soft atoms. Yeah, we literally call them soft atoms. Essentially what that means is the electrons are able to kind of squish and they're able to alter their electron distribution. The more polarizable an atom is, the better it's able to accommodate that negative charge. So although carbon and iodine have the same electronegativity values, the iodine's more polarizable than the carbon, and the negative charge ends up on the iodine. So really, the original rule I gave you actually still holds. If the atoms are the same, it's nonpolar. If the atoms are different, it's polar. But if your difference in electronegativity is too great, now it actually becomes ionic. Make sense? Okay. Well, that's how you tell the difference between polar and nonpolar bonds. So what does that have to do with polar and nonpolar molecules? Now we can talk about that in a meaningful way. So let's talk about that. So molecular polarity here. If the bonds are nonpolar, the molecule is nonpolar. That's simple. It's quite easy. All right. If your bonds are polar, it might be polar, it might be nonpolar if the bonds are what we call symmetrically distributed. What do we mean by that? Okay, well, here's a molecule. This is carbon tetrachloride, CCl4. Okay, and so it looks like this. What is the VSEPR formula for a CCl4 molecule? Well, it's an AX4. 1, 2, 3, 4 shared pairs, no unshared pairs on the central atom. What's the shape of an AX4? Tetrahedral. What's the bond angle on an AX4 tetrahedral molecule? 109.5. Right, just check it. Okay. All right, so we're going to draw it like this. It's technically tetrahedral, but this is not going to mess up what we're about to do here. Okay, so here we go. Are the bonds in carbon tetrachloride polar or nonpolar? They are polar bonds. Why are they polar bonds? Because they're bonds between different atoms, right? Okay. Is the molecule polar or nonpolar? Well, it depends. And here's how you tell. What we're going to do is we're going to draw little arrows on each of these bonds. Okay, we're going to draw the arrow toward the more electronegative element, put the little plus on the other side. So carbon or chlorine, which one's more electronegative? Chlorine, closer to fluorine in the periodic table. Carbon or chlorine? Carbon or chlorine? Carbon or chlorine. Okay? Okay, for those of you that had some physics, this is the way it works. What you see here are vectors. If you can add those vectors up and you get a resultant of 0, it's nonpolar. If you add those vectors up and you get any resultant of any length in any direction, it's polar. The direction tells you where the plus and minus are in the molecule. The length, or the scalar part of your vector there, tells you something called the dipole moment. And essentially what that is, that means how polar is it. Now, if you have a molecule with a high dipole moment, then it's highly polar. If you have something with a low dipole moment, it's not very polar. It's kind of like strong magnet versus weak magnet. Okay? Now, for those of you that had any physics, here's what we're going to do. We're going to put our little pluses and minuses in here. So where are my pluses? Well, they're here on the carbon. So that should be a partial plus sitting on this carbon right here. Okay? And a partial minus here. Partial minus, partial minus, partial minus. Okay? If you can go to one side of the molecule and go to the opposite side and see something different, it's polar. If you can't, it's nonpolar. So if I am right here, I see what? I see a partial negative. Here, I see a partial negative. Here, I see two partial negatives. Here, I see two partial negatives. Here, I'm kind of close to a negative and kind of far from a negative. Here, I'm kind of close to a negative and kind of far from a negative. Is there any side I can go to the opposite side and see something different? No. This is a nonpolar molecule. All right. Notice all my arrows are all canceling each other out. These bonds are kind of symmetrically distributed, and that's what makes it nonpolar. Okay? Well, here's a molecule we all know and love. This is water. Remember, that's an AX2E2. That's a bent 109.5. Okay, and looks a little something like this, bond angle 109.5. Technically, actually 105. Again, no lone pairs repel one. But okay, 109.5, close enough. Polar bonds or nonpolar bonds? Well, that's polar bonds. They're bonds between different atoms, oxygen and hydrogen. Polar molecule or nonpolar molecule? Well, it depends. So let's look at the bonds. So which is more electronegative, oxygen or hydrogen? Oxygen. Draw your arrow toward the oxygen, put your little plus on the other side. Oxygen or hydrogen? Oxygen. Draw your arrow toward the oxygen, put your little plus on the other side. So these hydrogens here on this side, this bond is partially positive. Over here on the oxygen, you're partially negative. Same thing here and here. All right, so what do I see if I'm right here? Well, I see a partial negative and a partial positive. What do I see over here? I see a partial negative and partial, so nonpolar molecule, right? What do I see if I'm up here? I see kind of a partial negative, right? what do I see down here? I see two little partial positives. Do you see that this side of the water molecule is kind of the negative end, and this side over here is kind of the positive end? It's kind of like a little magnet. In fact, I can draw one arrow that represents the polarity of this molecule, and it looks something like this. This is a polar molecule. It's got a net positive side and a net negative side. The electron distribution is not even, but it's kind of skewed on one side. It's a little side or top heavy in this case, I guess. And that's what makes it a polar molecule. So if you can see a net positive and negative side, it's polar. If everything kind of cancels out and there's no net positive negative side, it's nonpolar. All right? So nonpolar bonds, always nonpolar. Polar bonds might be polar, might be nonpolar. You got to check. All right? Now again, what if I had thought that water looked like this, where my two hydrogens were straight out and you had a pair there and a pair there? Well, you draw your arrows. There would be no net positive and negative side. Now, inside to out doesn't count. You can't do that. You can't say, well, the carbon here is positive, and I got negative on the outside. It's got to be one side or the other. Top, bottom, this way, this way. You can't say inside, outside. It's got to be one side or the other. If you drew it with a hydrogen here and a hydrogen here, it would be, you would think it would be nonpolar. But it's not nonpolar because the shape of the molecule looks like this. How do you know the shape of the molecule looks like this? Because it's an AX2E2, which is bent 109.5. How do you know it's an AX2E2? You've got to draw the dot structure. Have I said that enough in the last 3 videos? Everything keys on you drawing the correct dot structure. You've got to get that to get the shape. If you don't get the shape, you might miss whether it's polar or nonpolar. Okay, so get good at drawing dot structures. Okay? All right, well, let's wrap it up here. So what? Water's polar, carbon tetrachloride is nonpolar. Yeah, who cares, right? Doesn't really matter. Yeah, it does. Makes a big difference. Okay? Here's 2 places where it makes a difference. And there's more than 2, but hey, I've only got a few minutes left here. So one thing that makes a difference is in solubility. There's a general rule of thumb in chemistry that says like dissolves like. If I have 2 liquids and I want to know if they're going to be soluble or not, like dissolves like. Essentially, the more alike 2 things are, the more likely they are to be soluble in each other. What that means is organic substances, things that contain carbon, tend to be more soluble than organic solvents. Inorganic substances, things that don't contain carbon, are more soluble in inorganic solvents. But beyond that, polar molecules tend to be more soluble in polar solvents. Nonpolar molecules tend to be more soluble in nonpolar solvents. All right? So this is actually a liquid at room temperature, carbon tetrachloride. Here's water. If I took them, stuck them in a test tube, shook them up real good, would I expect them to mix really well? Or would I expect them to separate out into 2 different layers, like Italian salad dressing here? Well, this is an organic, nonpolar molecule. Water is what? It's inorganic, and it's polar. Are they very much alike? No, they're very much not alike. And so what will happen is if you put them together in a test tube, the water molecules will kind of congregate together. The carbon tetrachloride molecules will kind of congregate together, and they will separate according to density. The water has a density of about 1 gram per milliliter. The carbon tetrachloride somewhere around 1.36. So you will see a layer of carbon tetrachloride on the bottom of your test tube, and you will see a layer of water up there on the top. They don't mix very well at all. All right? And you can use stuff like that to predict solubility of all sorts of things. You have things like water, which is inorganic and polar. Then you have things like hexane, Leroy, which is also known as petroleum ether, which is kind of ironic. It's not really an ether. Those are nonpolar organic type solvents, along with carbon tetrachloride. And then you have polar organic solvents, like methanol and ethanol. And then you have polar aprotic organic solvents, like DMSO, tetrahydrofuran, things without something called hydrogen bonding, which is later on. But all sorts of things like that. In here, everything we deal with, like salt, is so polar it's ionic and it's inorganic. So there's a lot of stuff that goes into water. All right. But when you get to organic chemistry, it's not that easy. You have to worry about what solvent you're going to use as well as what you're going to react together. It gets a little more complicated. And one way you can tell is this rule right here, light dissolves light. So yeah, polarity does make a difference. Okay? All right. Do you remember we talked about this water molecule, and we said there was, when we were talking about like a sodium plus, say for example, in a water solution. And we said the good things about being a sodium plus is you got that noble gas structure. The bad thing about being a sodium plus is you've got a charge. And I can't bring you a jar of sodium plus because the principle of neutrality says that solids, liquids, low temperature gases have to be electrically neutral. Right? But I said there was something about that water molecule that's able to stabilize that positive charge to make it less of an issue than it ordinarily would be. And we said the same thing about anions in water, like a chloride or something like that. We said there was something about that water molecule that's able to stabilize that. So what exactly is that anyway? Well, it actually is the fact that water is polar, is why it works that way. So let me see if I can find you a picture real quick. Wikipedia. Wikipedia is always your friend, isn't it? Hopefully YouTube doesn't shut me down from using something from Wikipedia, but I think all they care about is like Rolling Stones tunes and stuff like that. But here's a picture of a sodium ion right here. And you see these little guys right here? These are water molecules. The reds are the oxygens, and the whites are the hydrogens. Notice that my partial negatives, kind of hard to see in this, but my partial negatives here are on the oxygens, and the partial pluses are on the hydrogens, kind of like we showed. Notice that the partial negative oxygen here is kind of attracted to this sodium plus here. And so my water molecules will align themselves and orient themselves in that way. Now, it's not a full chemical bond, but it's an attraction. Okay, and that's why it does that. What that does is it forms what we call a solvent cage. It forms a cage around this sodium plus. And this attraction here between this lessens this positive charge on this sodium. Does it make it zero? No, it doesn't make it zero. But is it a little less than +1 now? Yeah, it's a little less than +1. So you're violating the principle of neutrality, but not quite as much. The fact that you've got the nice noble gas structure wins out. And so yes, I can have sodium plus in a water solution. Can I have sodium plus in the open atmosphere? No, because there's nothing there to stabilize that positive charge. Now, what if water wasn't polar? Well, it wouldn't align itself like this. You wouldn't get that stabilization, and sodium plus wouldn't be soluble in water. See, sodium plus isn't soluble in carbon tetrachloride because there is no net positive and negative end of a carbon tetrachloride molecule. It's a nonpolar molecule. So just kind of go to the bottom of the test tube and just kind of sit there. Why are some things salts soluble and why are some salts not? Well, essentially what it comes down to is, it comes down to two things, really. It comes down to the lattice energy of the crystal structure. The lattice energy is how much energy it takes to tear apart all those little sodiums and chlorines that are all kind of connected together. If I have a high lattice energy, it takes a lot of force to get them apart. If I have a low lattice energy, it takes very little force. So essentially those little water molecules have to get in there and dig in, and they have to separate the sodiums and the chlorines. Imagine a chlorine over here. It's a negative charge. Well, these water molecules will actually line themselves up around the chloride there as well, only it'll line themselves up with the positive end around. So the opposite of this right here, and form a solvent cage there. If your two little ions can somehow break through their little solvent cages and meet each other in the middle, it's almost like a romantic comedy there, then you will find them at the bottom of the beaker. Got yourself an insoluble salt. But, on the other hand, if the water molecules are able to separate them and keep them separate from each other, floating around in solution somewhat stabilized, those are your soluble salts. And that's really what that entire chart back in chapter 4, what it comes down to, is can the water molecules separate them and keep them apart, or can it not? And water couldn't do this if it were polar. If it were not polar, and it wouldn't be able to stabilize these charges. And therefore, that's why salts are soluble in water, and that's why those ions can exist in water, whereas they couldn't exist in just plain air. So yeah, I explain things. It just takes me a few weeks to get around to it. So yeah, it does make a difference. It does make a difference. Okay? The other thing I will talk about, and I will let you go, is ice. Okay? Which is the more solid phase of water? Is it the solid phase or the liquid phase? Think about it before you answer that. If I take an ice cube and I put it in a glass of water, where does it go? Does it go to the bottom or does it go to the top? It actually goes to the top. The liquid phase is more dense than the solid phase. Now, is that typical of most substances? No. Usually the solid phase is more dense than the liquid phase. And of course, the gaseous phase would be the less dense phase there. But water is kind of peculiar in the fact that the solid phase is actually less dense than the liquid phase. In fact, water will actually get less dense as you cool it off until you get to one specific temperature, and that's actually 4 degrees Celsius. Once you get to 4 degrees Celsius, it actually starts getting less dense, and then it freezes, and it's less dense from there. So the most dense you can have H2O is in the liquid phase at 4 degrees. And that's actually where it weighs 1 gram per milliliter. When you measured the density of your water in that second lab, you found it was a little bit less than 1 gram per 1 gram, right? Per milliliter. Well, that's why you weren't at 4 degrees. So, what's going on there? Well, let me find you another picture here. Okay, you'd be surprised how hard it is to find a nice picture of ice that you can actually kind of see here. So I guess this will have to do. So here's a snowflake. So, what does it really look like? Well, it kind of looks like this. Notice that your reds here, these are your oxygens. The whites are your hydrogens. Notice that the molecules are lining themselves up in such a way that this oxygen here with these two hydrogens, this oxygen is attracted to this neighboring hydrogen, partially positive hydrogen, on this other water molecule. And on this water molecule here, its partially negative oxygen is being attracted to this partially positive hydrogen on this different molecule. These are intermolecular forces. All right, and all those little partial pluses and negatives that are kind of holding together, that's what constitutes an ice crystal. That's what water looks like. And so you get these kind of open hexagonal type structures here when you're making ice. Okay, now, why is ice less dense than water? Well, what have I got here? Look at all these holes in this structure. How much does a hole weigh? A hole does not weigh anything. But does it take up space? Yes, it does. So essentially what you've got is you've got these voids in this ice crystal which don't weigh anything, but they take up space, and that's what actually lowers the density. And so therefore ice is actually less dense than water, where your molecules are just kind of randomly associated together. So water will get more dense as you go to about 4 degrees Celsius, and then it actually starts getting less dense, and then it freezes over. And this is why ponds freeze from the top down instead of from the bottom up. Because the pond cools off, if the water gets colder, it sinks. And it will keep sinking until the water gets to be 4 degrees. And then once it cools down to 3 degrees, then the water stays where it is because it's water, see? And then it'll cool down to 3 and 2 and 1, and then it will finally freeze over. You see, a pond can't freeze over unless all the water in it is 4 degrees or less. If there's any water that's more than 4 degrees, well, as soon as it cools down, it'll sink, see? And more water will come up. But once there's no more water to come to the top, everything freezes over, which I guess is a good thing if you're a fish, because where do you live in the winter? Well, you live in the bottom. If the pond froze from the bottom up, and then the whole pond froze, well, you'd be flopping up there on top of the pond, you'd be dead. That's what you'd be. So yeah, I guess it's a good thing if you're a fish that water does that. And all that has to do with the fact that water's polar. If water weren't polar, you would not see that happen. So yeah, this bond polarity stuff does make a difference. Is there? All right, and this is how you tell. Okay, we're a little long on this one, I guess, but hey, we finished, right? So there you go. that is Chapter 7, so you're ready for a test. There's something about non-dissociation energy. We've already covered that. You're not responsible for that. Lattice energy. I kind of told you what it was, but I more than likely probably won't put much on the test on that. There's some stuff there about two nonpolar or two non-metal atoms form covalent bonds, and metal and non-metal atoms form ionic bonds. But I mean, geez, you already knew that. We talked about that a long time ago. So yeah, probably throw that in there, I guess. But other than that, that's pretty much it. So good luck on the test, and I guess we'll see you in the next chapter. So I guess it's time to quit. So